In this video, we will be discussing about discrete structures and the topic is set, relation and function. So what is set? Set is a collection of well-defined distinct objects and those objects or elements does not repeat. Suppose I have a set A, B and C. Here A is not equal to B, is not equal to C. This implies elements should not repeat in a set, right? And this can be written as X such that X belongs to R, right? This is set with the notation. Now what is cardinality? So cardinality means number of elements present in that set. So cardinality is represented by this mod A is equal to 3. This set has 3 elements, so cardinality is 3. And then null set. Null set is a set having cardinality 0, no elements, right? And then power set. So power set means all subsets of any set, all subsets of any set S including phi and S in itself, right? So what is power set? It means suppose power set of A, I have to write, it will contain this set contains all elements which are subsets, right? Subsets of these sets, and cardinality of power set is given by 2 to the power n, where n is number of elements present in set A, or n is cardinality of set A, right? Now what is subset? Subset means every element of, let's say there are two set A and set B, and every element of B is in A or it can equal to A, so it means it is subset, right? Subset. Now if I remove this mark from here, it means it is proper subset. It means it cannot equal to A, right? Every element of B is present in set A, but it cannot be equal to set A, right? Because A has some extra elements. Now, what is Cartesian product? So, Cartesian products mean set of all ordered pair A comma B, right? A comma B, where A belongs to set A and B belongs to set B, and this is what Cartesian product of set A and B, right? And then operations between two sets. Suppose I write A, set A, union set B. So it basically means union, right? Either my element should be in set A, either my element should be in set B. So how I can write this as X, right, such that X belongs to A, or either X can belong to A, either X can belong to B, right? Simple. And if I write A intersection B, it means X should belong to A as well as B, right? So here I will use AND. I hope you are getting it. And right, this is and difference A minus B. So what it means? Elements should be present, this element of mine should be present in A but not in B. So what I will simply write, X should belong to A but X should not belong to B, and this both conditions should be true. So I am using AND, right? And for complement, simply X does not belong to A. Complement is easy, right? Now I am discussing a question. I have to prove A intersection B complement is equal to A complement union B complement, right? So how can I prove this? First I can prove A intersection B complement is subset of A complement union B complement, and A complement union B complement is a subset of A intersection B complement, right? I can prove these two things separately, right? So what does it mean? Suppose I have any element x belongs to A intersection B complement. So when I remove complement here, that means x does not belong to A intersection B, right? This means I can also write this thing as x belongs to A intersection B, and I can also write, if I go here, right, this is intersection, so I can write this as x belongs to A, and sorry, when I using the what we have discussed in previous videos, this negation will make this as union, right? So it can be written like this, or it can be, here I am writing this as x belongs to A, or x does not belongs to A. This will also work. X does not belongs to B. This also work. This is what? Or, right? So I can say x belongs to A complement, or x belongs to B complement. Sorry, x belongs to B complement. And this thing, these and these are same thing. So I can write A complement union B complement, right? This I proved, and this is subset, right? And here the same thing I am going to prove. What can I write this as? X belongs to A complement, or x belongs to B complement, right? I can write this as, suppose I have a element x, and then I can write this as negation, right? Once I put negation, this will be and here it will be x does not belongs to A complement, and x does not belongs to B complement, which means x belongs to B, x belongs to A, right? And this I can write this as here, so it will be A intersection B whole complement. So in this way we can prove this, right? Next is principle of inclusion exclusion, right? So this is what we already studied in our propositions, right? We have already studied this. So there is a question: how many positive integers are less than equal to 100 and divisible by 4 or 6? Here or means A union B, right? My number should be divisible by 4, or my number should be divisible by 6. How many positive integers? Less than 100. So what I will do, suppose I have elements A and I have elements B, right? Now number of integers divisible by 4 less than 100, it will be simply, right, 100 by 4 equal to 25, and number of integers divisible by 6 will be simply 100 by 6, that is 16, right? There are 16 numbers which is divisible by 100, because once I do this 6, so I will take this 16 elements. Now what is happening when I will subtract this and this, right? When I will add this, I have got these numbers divisible by 4 and these divisible by 6. So I will also get that are divisible. Suppose there is a number y, it is divisible by 4 and this number is divisible by 6. So this is added 2 times. So I have to remove this 1 time. So what I will do, I will find those numbers which is divisible by both 4 and 6, and that number which is divisible by 4 and 6 both, I will take LCM. So LCM can be taken as 2. So LCM will be 12. So those number divisible by 12 I will subtract. So it will be, right, this is 8 not 9, 8. So I will add these two and remove this. This is my answer. Right. Now relation is any subset of Cartesian product of sets is called relation. Right. So any subset of Cartesian product, any subset, suppose I have A as 1, 2, right, and B as ABC, B as ABC, and A cross B will give me simply 1 comma A, 1 comma B, 1 comma C, 2 comma A, 2 comma B, 2 comma C. So what is relation? It is saying any subset of Cartesian product of sets, right? So subset, my subset is relation, right? Now what is S dot R? S dot R means, it means S connects R, right? I mean, it means suppose there are two sets, suppose there are elements A and B, suppose SR connects set A to set C, and what it means, if there exists some B where A comma B belongs to R, suppose A comma B belongs to R and B comma C belongs to S, then second element of R matches first element of S, right? So S dot R will be simply A dot C, for which there exists B such that A B belongs to R and B C belongs to S, right? So suppose there is a question on this, right? Suppose I have R from from 1 to 3 to 1, 2, 3, 4, and my R is, set R is 1, 1 obviously, and 1, 4 it is also clear, and 2, 3 it is also true, and 3, 4 this is also valid, right? And S is from 1, 2, 3, 4 to 0, 1, 2, and S is suppose 1, 0 which is valid, 2, 0 which is also valid, 3, 1 which is also valid, and 3, 2 this is also valid, and then 4, 1 this is also valid. So S dot R, AC for S dot R can be 1, 0. How? There is 1, 1 and here 1, 0. So S dot R can be 1, 0, and then there is 1, 4 and then 4, 1. So there can be 1, 1 also, and suppose there is then 2, 3, right? In R I have 2, 3, and in S I have 3, 1 and 3, 2. So I can have 2, 1 and 2, 2, right? And then I have in R 3, 1. In R I have, right, I have 3, 1. So in S I also have 1, 0. So I can have 3, 0, and in R I have 3, 4, and in S I have 4, 1. So I can have also 3, 1. So S dot R will be consisting of this, right? S dot R. And then reflexive, symmetric, antisymmetric, transitive, everything you know. Intransitive, for every a comma b and b comma c in relation R1 is a comma c also in relation R, right? This was actually relation from 1 2 3 to 1 2 3 4, this, and s from 1 2 3 4 to 0 1 2, this, right? Now yes, there is a question. Yes, there is a question. I am erasing this. So there is a question. Suppose a relation R on a set A is transitive if and only if R to the power n is a subset of R. So what this theorem says, there is a relation R on a set A and this is transitive if and only if R to the power n is subset of R, where n is 1 2 3 and so on. Now, what does R to the power n means here? This means relation R composed with itself n times. So it is not R to the power n, it is relation R composed with itself n times, right? Because R composed with R gives us R square. R composed with R square will give us R composed with itself 3 times, right? So suppose there exists a comma b which belongs to this set R composed by R itself. It will mean that there exists some a comma x which will belong to R and x comma a which also belongs to R. So if R is transitive, then R composed with itself n times is subset of R, right? So what is happening? A comma x belongs to R, x comma a also belongs to R. That means a comma a belongs to R, right? Or say suppose a comma b belongs to R and a comma c belongs to R square, then b comma c also belong to R, right? So that means R is transitive, a comma c belongs to R. That means R composed with itself 2 times is subset of R, right? Now using inductive hypothesis, suppose for R composed n times is subset of R and I have to prove R composed n plus 1 times is subset of R again. So what I will see, suppose AB belongs to R composed with itself n plus 1 times. This can be written as R composed n times multiplied by R, and there exists some element x belongs to A such that x belongs to R such that a comma x belongs to R and x comma b belongs to R composed n time. So R composed n time is subset of R and we know x comma b belongs to R because R is transitive, right? So it follows A comma B also belongs to R, right? Because R is transitive. So R composed n plus 1 time is subset of R again. This is how you will prove right. So this is all for this video.